Radio waves can be sent over 10,000 miles with no Earth curvature obstruction. So we can just send these radio waves out horizontally. They can be detected and received over 10,000 miles away. Radio waves are nothing more than non-visible light. So microwaves, radio waves, light, all the same thing, right? In fact, what we typically call light is just visible light. It's all electromagnetic radiation, and there's a huge span of frequencies. And that's what radio waves are. Okay, so you have the radio spectrum labeled there for you, right? As you actually get to 300 gigahertz up to 300 megahertz, that's the microwave range. And then you have that very small portion being the visible light. Electromagnetic radiation going out horizontally can be sent over 10,000 miles successfully, and was done in the early 1900s. In 1901, we had the reception of the transatlantic radio signals by Marconi. If you have this tower that's just, a few dozen feet up, and then you shoot a radio wave out, well, the curvature of the Earth is going to block the wave. So you can't send it 2,000 miles if you do the math, based on how high you're sending the signal out from horizontally, line of sight. Then the curvature of the Earth will block it at less than 200 miles. They're like, that's not going to work, bro. He's like, well, I'm going to try it anyway. First attempt successful, 2,200 miles away. So shot it like the Earth was flat, line of sight, radio wave was received 2,200 miles away. So they had to come up with an excuse, and that's where Oliver Heaviside came in, and they came up with the idea of the ionosphere. And they claim that the ionosphere is an area of the atmosphere that is ionized. Of course, ionized gas is plasma. There's a certain ionization of the gas at a certain layer in the atmosphere that reflects the radio waves back down. They came up with this to explain how the Earth is in fact a ball, even though the radio wave should have been blocked by the curvature of the Earth. This is where you get the idea of skywave propagation. You see the depiction here. If you send something out horizontally on a globe, what happens is it goes towards space because the Earth is dropping down and away from you. They claim, oh, well, it goes up, hits the ionosphere, bounces back down, then reflects off the ground, goes back up, hits the ionosphere, bounces back down, and it keeps bouncing down, up and down. And it said that radio waves topping out with the frequency of about 30 megahertz bounce off the ionosphere in what is called skywave propagation, depicted to the right. Very high frequency signals with frequencies above about 30 megahertz, quote, usually penetrate the ionosphere and are not returned to Earth's surface, and that's from an official source. This creates what is called a skip zone or a dead zone. So if you see the little triangles there, the area in between is where it couldn't be received. They say that the ionosphere tops out at 40 megahertz. If you have ionization and you send a radio wave, it'll reflect back to you if the radio wave is a lower frequency than the ionization. So say you have some plasma over here and the plasma is 40 megahertz. Well, if you send out a signal that's 40 megahertz or 39, so 40 and under, it'll reflect it back to you. If you send out a frequency that's 41 megahertz, it'll go right through it. So if it's a higher frequency, it penetrates directly through the ionization. And here I have, do microwaves bounce off the atmosphere? While lower frequency radio waves can follow the contours of the Earth and bounce off layers in the atmosphere, microwaves can only travel line of sight, typically limited to 30 to 40 miles on Earth's surface. Under normal ionospheric conditions, 40 megahertz is the highest frequency radio wave that can be reflected from the ionosphere. Well, here is the world record, a list of world record amateur radio transmissions. If you look all the way to the left, this is megahertz, it's the frequency. So we have all these above 106 megahertz. If you look a few columns over to the right, you're gonna have the distance in miles right here. And so we have 1,000 miles, 1,500 miles. We have all the way up to 2,500 miles. There was a 106 megahertz frequency radio wave sent 2,500 miles. Now these should be blocked at a couple hundred miles according to the globe Earth. Well, the problem here is, just like it says here, under normal ionospheric conditions, 40 megahertz is the highest frequency radio wave that can be reflected from the ionosphere. These are over 100 megahertz and happen all the time. This is not a rare occurrence. If the frequency is higher than 40 megahertz, it would penetrate directly through it, and in the globe paradigm, continue on to space. And here we have them, instead of going 200-300 miles maximum, we have them going 2,500 miles. That is direct physical refutation of a claim that the Earth is a sphere. You also have microwaves, and they have a significantly more narrow beam. There's such a higher frequency, they don't span out as much, and thus they have much smaller span of diffraction. We have microwaves depicted as orange and radio waves depicted as the gray one. You'll see you have the microwaves shooting out and then also the radio waves. This hill here is basically going to represent the curve of the Earth. If we send these radio waves out to the hill will block the radio waves because the hill is higher than the tower, right? But since the radio waves are spanning out so much wider, part of the radio waves will actually span out to above the hill, and then it'll go past the hill and then fill back in behind it. And this is called diffraction. The problem is the microwaves don't span out as much, so it can't get past the hill because it's not wide enough to even be diffracted around the hill. Microwaves travel by line of sight. Unlike lower frequency radio waves, they do not diffract around hills, follow the Earth's surface as ground waves, or reflect from the ionosphere. So terrestrial microwave communication links are limited by the visual horizon to about 40 miles. Now, we have them much longer than that, and of course the horizon shouldn't just be visual, it should be a physical geometric place, which means we should be able to do the math and know exactly where the physical curve of the Earth is. Doesn't matter where we visually see it. The microwave frequency range lies between 300 megahertz, 300 gigahertz. Beyond 40 megahertz frequency doesn't get reflected back by the ionosphere. It can pass through the ionosphere due to the microwave frequencies are not suitable for ionospheric propagation. Well, here we have them going 50 to 250 miles with a 99.9% success rate of reliability. That's a problem because it can't just be, oh, it just randomly scatters and we get it. Well, no, the signal strength would have to drop down almost completely, which they don't, and you wouldn't have a 99.9% reliability.